Thanks very much. Can you hear me at the back? Okay. So Sasha asked me to talk about LIGO and black holes. I know that Francois has already talked about black holes the previous week, so some of what I will say may repeat it, but I think it's okay for you to hear this twice, maybe from a different perspective. So on the slide now, you see a picture of one of the LIGO sites. This is a site in Louisiana in the desert, and you can see the configuration of the interferometer, which consists of two 4-kilometer long arms. And I'll talk a little bit how the interferometer actually works, what are the principles on which it's based. And the next slide, you can see the second LIGO interferometer, which is in the swamp in the state of Washington. And the second slide also shows the plan for my talk. So I'm going to walk you through a little bit of general relativity and black holes and gravitational waves, literally just to remind you, maybe those of you who haven't taken recently a course on general relativity. Then I'll talk about LIGO, the machine. The machine is amazing. It's an amazing physics experiment. It's really probably the most advanced physics experiment that mankind has ever created. This is my biased view because I was working on this when I was a PhD student at Caltech. And then I will talk to you about some things related to the black hole mergers that LIGO is measuring. We'll talk about different things, but in particular, we'll focus on a phenomenon which wasn't discussed last week, which is the gravitational wave memory. And this is a phenomenon which is an interesting general relativistic phenomenon, and there is a real hope that it will be measured by advanced LIGO if advanced LIGO reaches its design sensitivity. What is not shown in these first two slides is the third interferometer which is working. Who knows what this is? Yeah, by the way, I will ask questions. You know, this is a school, right? So I will point at people and ask questions. So somebody in the back 3 rows, what is the third interferometer that's currently operational? Virgo, yes. Do people know where it's located? Yes. Where in Italy? Italy is big. Yeah, near Pisa. Okay, in Tuscany. So Virgo has become operational a year ago. Exactly in the summer of 2017, Virgo has become operational, and this is important for my story. It was very lucky for the type of merger that Francois was talking about, GW170817, because it allowed to localize this merger on gravitational wave sky. And it was also important for one of the black holes, localizing one of the black hole mergers. Okay, so general relativity, very basic summary. So Einstein, of course, wrote his theory in 1915. And this theory relates geometry, which is represented by Einstein's tensor on the left-hand side. It relates it to matter. So on the right-hand side, you have stress energy tensor of whatever matter you have in the universe, represented, as we know, fundamentally by quantum fields, but more practically by bodies, fluids, solids, etc. Whatever you have in the universe is represented by the stress energy tensor on the right-hand side of that equation. Now, so the meaning of Einstein's equations is frequently summarized as matter curve space and warps time. But what is important for my talk, is that even without matter, general relativity can have very non-trivial solutions. Okay? And black holes is a solution of general relativity which doesn't have any matter. That's a very important point. So you typically need matter to make a black hole. So, you know, astrophysical black holes appear because of what? Can somebody tell me how they appear? Yes, and what happens at the end of stellar evolution? Yes, gravitational collapse of a star which has run out of nuclear fuel. We don't know exactly how supermassive black holes appear, but for the stellar mass black holes, we are pretty certain that due to the gravitational collapse. Okay, so you need some matter in order to create a black hole. But once a black hole is created, it's a pure vacuum solution. The matter is gone. The matter disappears in the singularity of a black hole. And what's left is a pure vacuum solution of Einstein's equation. And this is what it looks like. Okay, this is the structure of a black hole. You can see this is the structure of a rotating black hole. And actually, all stationary rotating black holes feature this metric, feature the Kerr metric. And this is called the no-hair theorem. So you can see several things on this diagram. So the first surface is, the most important surface is the horizon. The horizon separates inside of the black hole from outside of the black hole. And if something happens inside the horizon, the information about this is unable to propagate to the outside. Okay? So if your friend is falling into a black hole, your friend would not be able to communicate outside. So this is like a causal surface. Then, near the black hole, there is an ergosphere. Ergosphere is the region of the black hole which is drastically affected by the black hole's rotation. Okay? So the black hole is spinning, and it's dragging space and time with it. When you are inside the ergosphere, the light cones are inclined in such a way that the future of the light cone is pointing in the same direction as the black hole is rotating. In other words, if you are on a spaceship inside the ergosphere and your spaceship is infinitely powerful, okay, and you direct your spaceship to go in the direction which is opposite to the rotation of the black hole, you will not be able to do it. Inside the ergosphere, you're forced to be dragged in the same direction as the black hole is spinning. And this is one of the mechanisms by which the black hole is connecting, astrophysical black hole is connecting to the outside world, right? If you have some magnetic field, Francois was talking about MHD, magnetohydrodynamics. Magnetic fields create stresses. If part of the field lines are threading the ergosphere, then the ergosphere will exert magnetic stresses on the outside world and will launch jets and do other interesting things. So ergosphere is very important for region of a black hole for astrophysics. But fundamentally, this looks very, very simple. And this is represented by a Kerr solution in 1963. And all of the black holes in the universe, all of the astrophysical black holes look like that. I want to say that black holes are the simplest objects in the universe, right? Because they're described by, fundamentally, just by two numbers, the mass of the black hole and the spin. The whole map of the black hole spacetime is described by two numbers. If a black hole is the most simple object in the universe, it's a vacuum solution, doesn't require any fields, then I will ask you, what is the simplest dynamical process in the universe from this point of view? If black hole is the simplest static object, what is the simplest dynamical process you can have? Expansion. Yes, you're right. Okay, what is the second simplest? Which involves black holes, all right? That's not so simple, because collapse, you need matter, blah, blah, blah. Like, imagine that you're God and you have empty space-time and you like punctured it in some place and you have a black hole. It's a static object, all right? Then if I was God, I would just make a second puncture next to the first one. And you have two black holes, right? And on these black holes, they make some dynamical evolutions. Sorry about that. But anyway, there was an animation of a simulation of merger of two black holes. At the bottom, you see the gravitational wave which comes from this merger. Did Francois talk about the mergers of two black holes? Did did he show you these pictures last week? Who can say what are the 3 stages of this merger? The first stage is what? In spiral, yes. So what is in spiral? Okay, and you get a chirp, right? You get a characteristic increase in frequency and in amplitude. And what is the second stage? Come on, speak up. Merger, yes. And so what happens in merger?
So 2 black holes just merge in one black hole.
Yes, the horizons merge, right? So you get one surface. And what is this final stage of this signal?
So we have only one black hole, which somehow oscillates, maybe.
Yes, it's called the ring down. So the black hole which forms is very strongly distorted, okay? And then it oscillates, it makes several oscillations, and very quickly the oscillations decay because of the emission of gravitational waves. And so you can see these 3 characteristic periods, right? So this is the in spiral at first, then the merger is literally a few of these oscillations, and then there is a ring down. I'll show you this waveform later on as well. Now the gravitational waves which come from the merger, they have two characteristic polarizations. So this is hugely exaggerated, but it shows the effect of these gravitational waves on a circular cloud of particles, which are positioned in a plane which is perpendicular to the direction of gravitational wave propagation. And so the gravitational wave distorts these clouds of particles into the elliptical shapes. And you can see that just like there are 2 polarizations for electromagnetic waves, there are also 2 polarizations for the gravitational waves. And these are basically correspond to the direction of the axis along which these elliptical distortions occur, the so-called plus polarization and cross polarization. Now, how do we calculate the amplitude of this distortion? Okay, so h is the relative amplitude of this distortion. This is a typical notation. And for merger of 2 black holes, it's very difficult to model. You know, it took us a long time to learn how to do computer experiments which reproduce those waveforms that I showed you. But it is very easy to estimate what is the amount of this distortion. Basically, you have to just take the black hole size and you have to divide it by the distance from the observer to the merger event. Because these are 2 dimensionless these are 2 numbers, the only 2 numbers that you have in this problem. And if you want to form a dimensionless strain of the gravitational wave, you just have to divide one by the other. So it's very simple estimate. Now, if I want to give you the number for what you would expect for an astrophysical black hole, okay, so let's consider an astrophysical black hole. And before LIGO, we only had experience with X-ray binaries which contained black holes in our galaxy. So this is a cartoon of what this type of X-ray binary looks like. In this X-ray binary, on the lower left corner, it is assumed that black hole is sitting there. And this black hole is in the binary with a companion. Can be a white dwarf or can be a main sequence star. And they're sufficiently close to each other that the tidal force from the black hole is pulling material from the companion. And this material falls into a disk and forms this accretion disk, which is very bright in X-rays. And we see these X-ray sources in the galaxy, many of them, hundreds of X-ray sources in the galaxy, and also hundreds of X-ray sources in other galaxies. So from the motion of the companion, if you can monitor the Doppler shift of lines coming from the surface of the companion, you can measure the masses of these black holes that we have in the galaxy. And typical masses that we have are about 10 times as much as the Sun. So if we consider this mass of the black hole, 10 solar masses, and place it somewhere outside of the galaxy where you are realistically can expect to see this merger, then the amplitude that comes is very small. Actually, here I didn't take 10 solar masses. I took 30 solar masses because 30 solar masses was actually the mass of the black hole that merged in August of 1915. Well, actually, 2015 didn't merge billions of years before that, but that's when it was. But that's when this merger reached, the signal from the merger reached the Earth and LIGO has detected it. I'll show you later how this happened. Anyway, for 30 solar mass black hole, the characteristic size of this black hole is about 90 kilometers. The merger happened about 1 billion light years away from us. So the h, the strain of the gravitational wave, has to be something like 10 to the minus 20. So now, how do I calculate the displacements of the mirrors of LIGO detector? I have to take this h, have to take this strain, and multiply it by 4 kilometers, right, which is a separation between the LIGO mirrors. So if I do this, I get the displacements which are of the order of 10 to the minus 17 meters. Okay, so during the first detection that LIGO made, that was the displacement that the mirrors have experienced as a result of this gravitational wave. Who can tell me the size of the proton? 10 to the minus 15. So this is 1/100th of the size of the proton. How is it possible?
There's lasers.
Yes, there is lasers. But the mirror surface, okay, the lasers touch, the lasers are incident on the mirror surface. The mirror surface is made of atoms. Each atom is how big? 10 to the minus 10 meters, right? So you have 7 orders of magnitude difference between the atoms, the sizes of the atoms from which the surface is made, and the displacement that you have to measure to detect merging black holes in distant galaxies. Say again?
How many atoms are there in the mirror?
How many atoms? Well, you calculate the size of the beam, okay? The size of the beam, the radius is about, 7 centimeters or so. So you can calculate. It's a lot.
Probably it can compensate, like if you just take the statistics.
Yes. That's exactly what happens, is that you're not measuring individual atoms, but you're measuring a statistical average of the positions of those atoms. That helps you. Another thing which helps you is that you're only measuring it in a certain range of frequencies. You're not measuring the full displacement of these atoms, but you're operating in the range of frequencies where this displacement is small. Okay? But at first, the people that were doing this estimate, I'm just telling this to you because imagine yourself 40 years ago when you're thinking about doing this experiment and just making some checks whether this is completely crazy or not completely crazy. So most people, when they made these estimates, they arrived to the conclusion that it was completely crazy. Could never be done. Okay? There are textbooks where these arguments are made. The gravitational waves will never be detected because the displacements you have to detect are so small. So I'm just telling this to you so that you have some idea of what kind of visionaries the people that insisted that this was possible, what kind of visionaries those people were. There is another thing which I want to talk to you about, is that at those type of displacements, the mirrors, the test masses which are hosting the mirrors, they behave like quantum objects, okay? There's a massive 40-kilogram things, okay? And yet, at those sensitivities, they, observe Schrödinger equation, their centers of mass, their displacements. They behave like quantum objects. Let me prove this to you. So suppose I want to make the following mental experiment, right? Suppose I'm measuring I have some precision that I require, delta x, and I want to keep this precision for some interval of time, which I call tau, okay? And I model this by making a couple of measurements. First at the beginning of the interval of time, and the second measurement at the end of this interval of time. So when I make the first measurement, delta x results in the perturbation of momentum, okay? By Heisenberg uncertainty principle, it's h bar divided by delta x, okay? Now, the perturbation of momentum, this is the random perturbation of momentum, after time tau will produce a perturbation in displacement, right? An uncertainty in displacement. So the total uncertainty is a combination of the error of your measurement, okay? Initial error of your measurement, and the random perturbation momentum that you made as a result of this measurement. So if you add this in quadrature, like this, you see that there are two components. One component is delta x squared, and then delta p is inverse proportional to delta x, okay? So you can optimize this expression by choosing the right sensitivity delta x. And if you optimize this expression, you get the minimal, the best you can do for making this quantum measurement is a very simple expression, square root of twice h bar tau divided by the mass, okay? And this is called the standard quantum limit for position measurement for free masses. It was actually discovered here in Moscow in 1967 by Vladimir Braginsky. But now it's a very well-known thing which is used all over, quantum measurement theory, quantum optics, etc. It's a very simple expression, but if you compute this expression for the test masses, okay, remember you're measuring gravitational waves with characteristic periods of, 1/10 of a second or so. So you want to maintain this precision for, say, 1/10 of a second. You have 40 kilograms of mass, you have h bar. You have all the information you need to make this estimate. If you make this estimate for 40 kilogram mass, you get 10 to the minus 18 meters, which is, just one order of magnitude below the amount of perturbation that was caused by gravitational wave, which came from merging black holes, GW 150914, a billion light years away. At the design sensitivity, LIGO will be operating at this quantum limit. It's not quite there yet. It's about a factor of 3 off. Okay, by design sensitivity, LIGO will be reaching the standard quantum limit, which comes from Heisenberg uncertainty principle operating on 40 kilogram macroscopic masses. It is quite an amazing experiment as a physics experiment. So let me talk a little bit about the design of the instrument. So it's a simple Michelson interferometer in some sense, but in other sense, it's not so simple. So you have two arms. Each arm, like I said, is 4 kilometers long. And you have a beam splitter which splits light coming from the laser into two components. One component goes into one of the arms. The other component goes into the other arm. Then the frequency of the light is tuned so that you are in optical resonance inside each of these arms. So these arms are pumped on resonance. See these big beams? They're pumped on resonance by the laser beams coming from the laser. Then light comes back out from these cavities, recombines with the beam splitter, and if there is no gravitational wave, if this length of the two arms are equal, then light just goes all the way back to the laser. if the gravitational wave comes, remember the length of the cavities, remember those deformed ellipses? Think about what it does to the cavities. The length of these cavities will be deforming in counter phase. That means that the phases of light coming from these cavities will be disagreeing with each other, and some of the light will be leaking down into the photodiode, which is operating at the so-called dark port. So when you have gravitational wave, then the photodiode starts seeing something. Okay? So that's the basic idea of how this interferometer works. Of course, the big art in this and the big question in all of this is how to reduce the natural noises in this interferometer to a level which allows you to measure 10 to the minus 18 meters, 1,000th of the size of the proton. Okay? How do you do that? And I listed here some of the, illustrated here some of the noise sources that LIGO people have to deal with. Okay, so let me just walk you through some of these noises. The first one on top is seismic vibration. All right? We are here, the ground is moving. The ground is moving, typically fractions of a millimeter or so. These are big movements compared to the sensitivity we need. So you have to have multiple stages of mechanical isolation which reduces the seismic motion of the ground. Okay? These are mechanical filters, several stages of mechanical filters. Then you have thermodynamic mirror surface movements. Okay? For us, if you look at the mirror, it looks completely smooth. But on the scale of 10 to the minus 18 meters, it looks like an ocean, okay? Moving waves, the surface is breathing. The shape of this test mass which supports the mirror is deforming, fluctuating. So these are just fundamental thermodynamic fluctuations of the mirror shape, one of the major sources of noise in LIGO. Then, light has quantum nature. Light is not a classical sinusoid wave. It consists of photons. So the sinusoid, it has some noise in it, quantum noise in it. And so you have shot noise, which is the quantum fluctuations in the light. And then what's also shown in this figure is that look at those clouds of gas. And those clouds of gas are crossing the beam. And of course, when they cross the beam, the clouds of gas, they have some index of refraction. Random crossings of the beam will cause fluctuations in the phase. That is why you have to have deep vacuum in this 4 kilometers, okay? Because if you don't have deep vacuum, the index of refraction inside the beam is going to fluctuate like crazy, and you will not see anything. So you have to go to very deep vacuum. Okay, this is what the suspension looks like, and this is another interesting thing because the idea for how to, these are big ideas in this field. How to suspend 40-kilogram mirror on a thread so that it's nice and works well. So the big idea here was to use fused silica and to also you can see that this at the bottom right. The fiber is glued onto this elongated, pulled, I don't know how to call this. You see this kind of conical shape which is pulled from that support. So it took a long time to zero in on this design. And actually some of the key ideas also came from Braginsky's group in Moscow. And they were later developed further and implemented by Jim Huff and Sheila Rowan in Glasgow. So these are what the mirrors look like. Okay, now this is the last slide that I'm going to show on the instrument side, just to show you what the noise curves conceptually look like. Of course, in reality, they look a bit different, but these are the products of calculations of what the noise curves look like. And we have seismic noise at low frequencies. In the middle frequencies, you have the thermal fluctuations, the thermal noise. you can see a fundamental quantum limit on this diagram, which actually, and the shot noise, the quantum nature of light, is coming in at high frequencies and is not letting Francois see his merger of neutron stars, right? If it wasn't for the shot noise, Francois could actually see the two neutron stars touching each other and very high, producing these high frequency gravitational waves. But they're all buried in the, this high frequency gravitational waves are buried in the quantum fluctuations of light itself in the interferometer. Okay, so I want to now get back to, this is just also for historical significance, because the guy that invented this whole scheme and calculated all the noises is called Ray Weiss, one of the 3 Nobel laureates in physics last year. And so Ray Weiss, when he started thinking about how to detect gravitational waves, he made this kind of drawing. He wrote a paper, but he didn't publish it. He didn't publish a paper because he thought, what's the point of publishing a paper without any results, right? You have to wait until gravitational waves are detected, and then you can publish it, right? That was like 1972, I think. This is a completely iconic paper in this field. Of course, it's freely available. Everybody has read it, but it's unpublished in any scientific journal, right? So in this paper, apart from coming up with this general topology, he also, he thought, the power of human thought, he thought of all the sources, all the possible sources of noise that you could have in the interferometer. Sorry, you can't see this very well somehow. But all these words like mechanical thermal noise, radiation pressure noise, all these things, this is what the LIGO instrumentalists have been talking about for the past 30 years. And these words were said first by Ray Weiss. Okay, now the detection of a pair of black holes happened in September 14, 2015. On the left-hand side, you see the power in the 2 interferometers. One is the upper interferometer is in Hanford in Washington, and the lower interferometer is in Livingston in Louisiana. And you can see that this was the first time that both interferometers had power inside. Both interferometers were locked. And literally, as soon as you had the lock, GW150914 has arrived. And that was like a huge lucky coincidence. A couple of hours after the interferometers were unlocked, you had this huge signal. So this is what it looked like, this signal. In one of them was in Livingston, exactly the same signal in Louisiana. And in terms of Fourier transform, you can see this characteristic chirp signal, right? Frequency versus time. This is at each moment of time. You have a little window. You take a Fourier transform. You plot this Fourier transform on the y-axis, and you get this time-frequency diagram. You see this characteristic chirps. I wonder if I can play a movie. Probably not. Okay. So this is audio representation of this chirp. Can you hear it? Could you hear it?
Yeah.
Now, by now, there are 5 published mergers, okay? So 5 black holes that are published by LIGO collaboration. GW150914 is the first one up there. And then there are 4 others. According to LIGO collaboration, they haven't yet published everything that they have, so there may be more coming out from the second run, okay? So everything was published from the first run, but the second run, not everything was published. Because, why do you think not everything was published? What ideas do you have? Say again?
It takes time to process the EM forward.
Yes, I think you're on the right track. But somebody has some more precise idea? Because as the second run was finishing, LIGO detected a merger of two neutron stars that Francois was talking about. And the whole collaboration went completely crazy. You know, it was working full time on finishing, you know, this analysis for GW170817, which was an incredible thing, you know, the best observed astronomical event. So they basically didn't have time for anything else. So some of the black holes are still remain unpublished. Okay, but what have we learned from it? One of the most important things that we learned from these mergers are the masses of the black holes that we're merging, and these masses are plotted on the y-axis. And just for comparison, also you see the masses that you get from X-ray studies of black holes and binaries in our galaxy. And you see a very interesting thing is that the black holes, by the way, so the x-axis has no significance, but the y-axis shows the masses of these merging black holes. And you see that, interestingly, many of them, actually 4 out of 5 of them, have components which are significantly more heavy than the black holes that we see in the galaxy. Okay, and this is one of the big puzzles in the black hole astrophysics. There are ideas, but certainly, you know, it's one of the big puzzles why the black holes that LIGO is seeing merging and giving gravitational waves, why they're 3 times more massive than the black holes that we see in the galaxy. You know, and it's a very, first of all, these are very precisely measured masses, and second of all, that's a very substantial difference, even by standards of astrophysicists. Now, we also know their locations on the sky. So this is a representation of the sky, and you can see that the locations are not so well determined. Now, who can tell me why the locations for many of them are kind of stretched into this kind of circles?
Because it was seen only by 2 detectors?
Yes, there were only 2 detectors, right? And 2 detectors mostly, not completely, but mostly localized using time delay between the arrival of the waveform. And if you're only using time delay, you're basically singling out a cone in the direction space. So that's why you have this kind of elongated circle-like regions on the sky. Now, why do you think GW170814 and GW170817, why do you think they're different? Why are they so well localized? Yes, because Virgo is running. So GW170814 is the first detection that Virgo took part in, so 14th of August 2017. And you can see the Virgo doesn't have as high sensitivity as LIGO, maybe a factor of 2.5, you know, worse than the sensitivity of LIGO. But just by the fact that Virgo detected something and could give the time delay already helps hugely to localize it on the sky. And of course, this is very important for other astronomers who can just then point their telescopes in that region of the sky and look for electromagnetic counterpart. Now, GW170817 did not get detected by Virgo, and yet it helped localize it. Why? Because the astronomers, gravitational wave astronomers, they could use the information that Virgo did not detect anything, and they knew very well where the dark spots, or the blind spots for Virgo were, okay, on the sky. And so that meant that that signal had to be located in one of the blind spots, and that helped localize GW170817 on the sky very well and allowed electromagnetic observers to follow up and find all this wonderful kilonovae that Francois was talking about. Okay, so where did GW 150914, this is the first binary of black hole. How did these black holes find each other, and other 5 binaries, how did they find each other? Why did 2 black holes show up next to each other and merge? Remember, I said that if I was God, I would just make 2 punctures next to each other and see what happens. Well, how does it happen in real life? And there are basically 2 ideas for how these things may happen. The first idea is that if you look at massive stars, which we think are the progenitors of the stellar mass black holes, about 70% of all massive stars that we observe are members of binaries. And that's quite a remarkable statement. And moreover, they're members of quite close binaries. So massive stars, they like each other very much, and they like to have companions which are kind of equal in mass. And then as a process of quite complex stellar evolution, if you take a binary of massive stars, then by a complicated sequence of events, remember each of the stars is evolving, is expanding, going off the main sequence, etc. Sometimes there's 2 massive stars, they have a common envelope. These are processes which are not very well understood from theoretical point of view. But we know that sometimes, we know from studies of binary neutron stars, we know that sometimes 2 massive stars give rise to 2 compact objects which are located close enough to each other that they actually merge due to emission of gravitational waves within the Hubble time. So this we know. And it is quite plausible, and you can make plausible scenarios of how 2 massive stars which are located next to each other, how they lead to 2 black holes which are located next to each other. The second type of ideas for how this may happen is if you have a dense cluster of stars. For example, if you have a very compact globular cluster with a collapsed core of a globular cluster, then what can happen is that even if you don't have black hole binaries to start with, because black holes are heavier than all the other stars in the cluster, they sink to the center of the cluster, they sink to the bottom of the potential well. Just like the tea leaves, they sink to the bottom of the glass. They push out the water molecules. The same idea, black holes, because they're heavier than other things, they sink to the center of the bottom of the potential well. Then they find each other, and they form tight binaries through dynamical processes. And this gravitational processes. And this is very well modeled on computers. This is basically Newtonian mechanics with a little bit of relativistic corrections. And indeed, plausible models predict formation of black hole binaries. So this is another class of ideas. And it's currently not understood. It's an open question which one of these models, or maybe there is some other model that actually make mergers of binary black holes. It's an open question. It's for you guys to solve, right? Okay. Are there any questions about these things? Because I want to talk about something completely different.
So do these 2 processes do they still occur on similar timescales, or do they predict different timescales?
There are 2 groups of people, 2 groups of astrophysicists. One group believes in just binary massive star progenitors for binary black holes. The other group believes in stellar cluster giving rise to these binaries. Both groups of people claim that they can explain all the observations. But for both of the scenarios, there are considerable uncertainties. There are considerable not understood details, right? For example, in particular, for the scenario where you have 2 massive stars, people don't understand what exactly happens when the stars go off the main sequence, and expand, and then the envelope of one star engulfs the other star. The dynamics of the stage is very uncertain. People don't understand very well the processes inside single massive stars. What is the effect that the rotation has, etc. So these are things which are not very well understood. And okay, that's all I can say. But because the scenarios have plenty of parameters, right? Free parameters that can be tuned. The modelers are able to say, yes, we can make all of the black holes using these scenarios. With global clusters, the gravitational dynamics is very well understood. Like I said, it's just Newtonian dynamics. But what is not well understood is the population of globular clusters throughout the universe, the type of globular clusters that can give rise to this phenomenon. That's unknown. Other questions?
Why globular cluster don't have a central massive black holes in the center?
Well, I don't know. Maybe they do. But where would it come from?
Well, I think they're not found.
They're found?
No,
they're not found. I think...
Typical X-ray emission, typical signature of an activity in the center of globular clusters.
Right. So certainly inside a globular cluster, people have never seen an intermediate mass black hole which is accreting. But there are claims in the literature that from dynamical modeling of movements of stars in the central parts of globular clusters, some people make a conclusion that there must be a dark mass. There must be some concentrated dark mass which is attractive to interpret as intermediate mass black hole. Now, these claims are disputed. So the way in which these claims are disputed is that some people say maybe it's not a single black hole, maybe it is a small cluster of normal stellar mass black holes, or maybe the velocity measurements of stars have enough uncertainty that you can't make this from conclusion. So I would say this is not a settled question whether globular clusters have intermediate mass black holes or not. There are claims both ways in the literature. Okay, if not, then I want to move to a different topic, which is gravitational wave memory. Okay, so it's a particular type of relativistic effect which was predicted a long time ago, and for a long time ago it was thought to be completely unobservable. It was thought to be just a curiosity of general relativity. But I think people are now realizing that there is real hope to see gravitational wave memory and to measure it using both LIGO and probably LISA. A little bit less likely using pulsar timing arrays. So these are gravitational wave experiments. So let me walk you a little bit through the physics of gravitational wave memory. Okay, well, first of all, let's look at this waveform again. This waveform consists of several components, and the type of waveforms that I was drawing before is the black one, okay? So the black one, like I said, consists of 3 stages. There is the in-spiral stage, there is the merger stage, and then there is the ring-down stage. The ring-down stage is where black hole is shaking off all the sphericity, and they all leave as gravitational waves. Now, these waveforms that people show is a lie. They're not true. And the way in which they are not true is that there is the gravitational wave strain doesn't come back to its original value, okay? It comes back to a different value. So the residual gravitational wave strain. If people were showing you correct waveforms, doesn't go back to 0. And this is called the Christodoulou gravitational wave memory. So typical waveforms that are shown to you, they don't have this component. Now, this component is small. I deliberately, when I was making this figure, I deliberately exaggerated it by a factor of 4 or so. So you have to imagine that this shift is smaller by about a factor of 4. So typically this shift is about 1/20th of the oscillatory, the maximum oscillatory amplitude of the gravitational wave. Okay? Now different parts of these waveforms will tell us different things about relativity. You know, this is relativity in its purest form. No matter, just extremely warped space-time in a very dynamical regime. So the in-spiral will tell you all about the post-Newtonian physics that you want to know, what the horizon, so when during the merger stage, the total horizon area grows according to the Hawking theorem. The total horizon of area has to always grow in the same way as entropy always grows. And then in the final ring down stage, if you manage to measure the frequencies of quasi-normal modes of the black hole, all the ring down frequencies, okay, you will be doing black hole seismology, just in the same way as you're doing seismology of, you know, the Earth or seismology of the stars. In principle, there is potential to do black hole seismology. Of course, black hole seismology will tell us about the structure of a black hole and possibly, you know, create a proof of the Kerr metric. Maybe Kerr will get a Nobel Prize if people indeed confirm that using black hole seismology, that Kerr metric is correct. Now, what does memory tell you? I will show you in a second that memory tells you about the gravitational field which is created by gravitons themselves. Okay? It's a gravitational field which is created by the flux, the energy flux, which is generated by the gravitational waves themselves. So let me walk you through this step by step. So at first, so memory, again, was discovered in its original form in Moscow by Zeldovich and Polnarev. Although the Christodoulou memory is a huge step from the original ideas about memory, and Christodoulou was a mathematician, actually. He wasn't even a physicist. He was a mathematician that was working in Princeton. So let me tell you first about this type of memory, the original discovery in 1974 by Zeldovich and Polnarev. It's a very simple thing, actually, and you should all understand it, right? If you look at if you open the standard textbook on general relativity, and you look at the chapter on how gravitational waves are produced, you will see the following formula. Roughly speaking, that the strain of the gravitational wave, to compute the strain, you have to take the quadrupole moment of the system that is producing gravitational wave, take a double derivative of the quadrupole moment, and divide by the distance. Okay, this gives you the strain of the gravitational wave. And I neglect all the g's and c's. I work in units where g and c is 1. Now, consider now that you have an explosion in cosmos. Okay, you have some compact body, it explodes, and the fragments are flying in all directions with constant velocity. Now, the quadrupole moment of each of this fragment is quadratic with time, right? Because remember, the quadrupole moment is a product of two coordinates, right? Each coordinate is linear with time, so the quadrupole moment has to be quadratic. So q scales as t squared. If I take q double dot, that's a constant. That means that each explosion in the universe, which is anisotropic and has fragments which are flying in all directions, it has to create a constant distortion of space-time, which persists forever. It's a very simple consequence of the quadrupole formalism. Okay, so it was a very simple discovery. Actually, Zildovich and Polnareff, they were calculating the following problem. They took two stars which were having a hyperbolic flyby. So two stars are coming in some direction, then they deflect their trajectory, then they're coming out along a different direction. And they were computing gravitational waves, and they noticed exactly this thing, that gravitational waves the strain did not go to its original value. The strain went to, became different value than it was before, precisely because of this effect. Okay, so very simple, almost like high school physics kind of discovery, right? Now, what was the insight of Christodoulou? Well, actually, Christodoulou's paper is very difficult. I cannot read it, and no high school student can read Christodoulou's paper. But Christodoulou realized, and it was explained to the world by Thorne. So Thorne's paper is very easy to read. So Thorne wrote a paper which explained Christodoulou's paper to the world. Okay, so in Thorne's language, what Christodoulou found is that if you, instead of the fragments, if you have gravitons, okay, or, wave packets of gravitational waves, each of these wave packets acts in the same way as the projectiles that I had before, right? So before I had projectiles, but now think of them not as like material bodies which are flying away from an explosion, but now think about, say, a merger of two black holes. And this merger creates anisotropic flux of gravitons, anisotropic flux of gravitational waves. And this flux of gravitational waves, okay, when people ask you what is a gravitational wave, the typical answer you hear is gravitational waves are ripples in the curvature of space-time, right? But gravitational waves are not just ripples in curvature of space-time. They're ripples in curvature of space-time which carry energy and momentum. And this is like, from the physics point of view, this is a crucial point. Because gravitational waves carry energy and momentum, in some heuristic sense, they're like, projectiles. They're like bodies which are moving with the speed of, relativistic velocities. And so they, according to the same logic, create a constant distortion in space-time. So that is the origin why this merging waveforms, they don't go back to the original value of the distortion. Okay, they go back to a value which is slightly different. And this is a nice picture that one of my collaborators did, explaining gravitational wave memory to his son, who is 5 years old and plays with Lego. So this is the explanation. This is what gravitational wave memory will look like for LIGO. So you have, if without memory you have LIGO in its original shape, and with the memory you have some constant distortion of space, and so one arm is longer than the other. Okay? So that's the effect of memory on LIGO. Yes?
So this is permanent?
The distortion of space is permanent, but this figure that my friend made for his son is wrong. It has an error, and I want you to tell me what this error is. No, forget the letters. I mean, is it plausible that really you have a burst of gravitational waves, and then the distance between mirrors in one arm is different from the distance between mirrors in another arm? That's impossible. Why do you think that's impossible? A very simple reason. Come on.
I think I understand because, If you imagine that your Lego models are individual atoms, the number of atoms doesn't change. It will restore the size of the arm.
Yes. But I want a more concrete answer. What is exactly going to restore the size of the arms? In the LIGO in particular, in LIGO detector. What happens? Yeah, it's suspended. These mirrors are suspended on wires. They're penduli. If you do this, if you push the penduli away and then let them go, they come back to the original point, right? So this is wrong. This cannot happen. You have always restoring force. Even if you try to change the length, you always have restoring force from the penduli. And yet, this effect is measurable. Okay, I'm telling you, this effect is measurable. So how can this be? Yes. There is a characteristic time. See this push that happens. Can you see my cursor? So this push that happens, it happens over some characteristic time scale. And it happens basically during the last few orbits. As these black holes come to each other closer and closer, there is a ramp up and there is a push. So this push has all kinds of frequency components, okay? Yes, it has a DC, it has a constant component, but that means low frequencies. But it also has frequencies which have the time scale over which this ramp up happens. And this time scale is quite short. Now it's literally several Schwarzschild crossing time scales, okay? Last several orbits. So, 10 milliseconds or so. And this is within LIGO band. So, in principle, a LIGO detector will be sensitive to it. It will not be sensitive to the low frequency part of this. This original thing that I told you, there is a permanent distortion of space-time. Yes, permanent distortion of space-time happens, but LIGO is not sensitive to it. Because LIGO is not sensitive to permanent things, right? LIGO is suspended. You have real penduli. But the transition between one distortion and the other distortion has all frequency components, and some of them are within LIGO band. Okay, and you can detect that. So this is just fun. Keep likes this picture. Okay, well, how much time do I have? 5 minutes. There are some technical aspects of this work. The interesting technical aspect, I won't show you any more slides. I will just say, it turns out that this distortion, or this kick that you get from memory is not strong enough for LIGO to detect from individual event, okay? It's kind of, it has signal to noise which is less than 1. So it's not detectable from a single event. So you have to be a little bit more clever to measure the memory. You have to ask the following question. Does the universe have memory, or does the universe not have memory? And then you have to compare these two different hypotheses. One hypothesis is that all black hole mergers don't have memory, and the other hypothesis is that all black hole mergers have memory. If you're comparing these two hypotheses, then you can accumulate information from multiple events, okay? When LIGO becomes operational and it's design sensitive, it will measure hundreds of mergers per year. So you can use multiple events as a source of information to compare the two hypotheses. And so you can show that you need about 40 or 50 well-measured mergers to detect a sign of memory. So it will take a while, and these mergers have to be quite strong. They have to be, at the same level, level similar to GW15 or 914, which is the first event that LIGO measured. But in the end, I personally believe that after about 5 years of operation of advanced LIGO, we will be able to claim the existence of memory. Not detection of memory in some individual event, but the existence of memory in the universe. Okay, let me conclude. I'm going to skip through some slides, and let me just say that we live in a pretty wonderful era, not just for study of neutron stars, but also for study of dynamical geometry of space-time. Some people believe that there is kind of an emerging field of theoretical physics, which they call geometrodynamics. Geometrodynamics is dynamics of space-times without matter, like merging black holes and wormholes, black holes, cosmic strings, things which don't really require matter. It's just dynamics of very strongly curved metric. And I want to impress on you that LIGO and Virgo are amazing machines, and that they need to operate at a macroscopic quantum limit for the test masses that you have on a detector. And this is almost achieved, and it will be achieved. That I want to impress on you that we're already learning some new astrophysics from the detected black hole mergers. So the detected black hole mergers are 3 times heavier than the ones we see in our galaxy, and it's a puzzle. Okay, we don't really know what happened. We don't really know how these black holes form. We don't really know how the binaries of such black holes form. This is a question that, for you to solve, for the new generation. I think we have much to learn about the origin of these black holes, and also about the relativity in strong field regime, which is represented by this nice artistic drawing, which has very strongly curved space-time. And as an example, I believe that gravitational wave memory is an interesting thing and potentially measurable from an ensemble of black hole mergers within the next, say, 5 years. Okay, so that's all I have to say. Yes?
What are the implications of the existence of gravitational memory?
Well, I don't know how to answer this well. What are the implications of the existence of other relativistic effects like dragging of inertial frames or of gravitational redshift? What are the implications of that? These are very non-trivial predictions of general relativity. And I believe that there is intrinsic value in, in confirming their existence. Everybody believes that dragging of inertial frames is real. It's a prediction of GR, but it is important to detect it. Okay, if you can identify some non-trivial effect, it is important to detect it. I think the implication for non-detection of memory are huge, but because that means that something is wrong with our fundamentals. Yeah.
Does that memory also have the polarization? Would we see the memory of this motion if we don't see the motion itself?
Can you repeat the question?
So we see gravitation waves from the motion with some polarization.
Yes.
So what about the memory?
Yes, memory, that's a very good question. Memory has polarization. It has a linear polarization. And this polarization is related to the polarization that comes from the merger. You can think about this in this way. When you have a merger of 2 black holes, most power comes in the direction which is perpendicular to the plane of the merger. okay, because this is where the amplitude of gravitational wave is the strongest. So you kind of have two broad jets of gravitational wave. I mean, they're not collimated jets, but they're broadly collimated in the polar direction. And so, and this is, you know, these are your projectiles. So your projectiles are, roughly speaking, flying perpendicular to the plane in which the merger happens. And that will also be the direction of your polarization. So you can see the connection now, right? Both of them, both the polarization of the main signal, the AC signal, and the polarization of the memory are related to the orientation of the merger plane. Yes?
And also, we was shown that there is at least 6 events, gravitational wave events already was observed.
5.
5, okay. And the amplitude of this memory is 1/20th of the gravitational event.
Yeah.
So it seems that it already should be seen at 1 or 2 signal levels.
Not quite, because the frequency band is not very the frequency. Yes, the amplitude, you're right about the amplitude, but the frequencies of AC mergers, they're much more favorable to detection than the characteristic frequency of the memory. So they differ in this way.
I was wondering, so they need to do they need an ensemble of mergers?
Yes.
Like this, but wouldn't this strain, the gravitational memory strain, wouldn't it be different for each merger? So can
Yes.
you do this?
Yes, that's right. So that's a very good question. However, we are talking about the mergers which are very strong. And so for each of this merger, the parameters of this merger, the orientation of the plane of the in-spiral, will be very well measured from the AC part of the signal. So in each of these mergers, there will be prediction of what the memory should look like. Okay, and it's an ensemble of looking for confirmation of these predictions. That this is what you will be testing for.
And also a follow-up question. So can the strain be both that it extends it or that it contracts? Like the final strain, could it be an extension in the direction, and can it also be a contraction?
So gravitational waves, memory is a gravitational wave. It's a DC gravitational wave. And gravitational waves, they have this feature that they always transverse. So for example, if you have a spherical cloud of particles and you have a gravitational wave which is coming from some direction, the distortion of this cloud will be only in the direction which is perpendicular to the direction of propagation, right? So all the particles will be moving in directions which are perpendicular to the direction of propagation. So gravitational waves are never longitudinal. They're always transverse, just like electromagnetic waves. Except for electromagnetic waves can be longitudinal in the dielectric medium or in plasma. With gravitational waves, these things don't exist. There is no gravitational wave dielectric. So gravitational waves that are always transverse. And the distortions are always in the direction which is perpendicular to the direction of propagation. Now, the distortion is such that it contracts along one of the axes and it extends along the other axis. So the total, if you like, area of that ring that I was showing on the slide, the total area of this ring is conserved.
Okay, so if you have enough events, the memory effect should cancel out.
Well, like I said, you're not looking for cumulative memory effect. You're not looking for like cumulative distortion of some cloud. Instead, you're checking for an ensemble of predictions that you get from each of the signals, right? So from each of the signals, you have a strong prediction of what memory should be, and then you're testing whether it's there or not. And generally, you will, for each of this thing, you'll get something like signal to noise 0.2, let's say, evidence for the presence of the memory. But once you have 100 of these events, okay, the ensemble of 0.2 signal to noise, but it's signal to noise in favor of a single hypothesis. So you have to multiply it by square root of n. If you multiply 0.2 by square root of 100, right, you get signal to noise of 2. And that's when you start building, you know, evidence for the existence of the memory. Other questions?
Just a curiosity about memory, and wouldn't you expect that, like in a quantum system, after a while you expect like a sort of decoherence of the strain due to the gravitational wave memory, because I mean the gravitational signal due to the gravitational signal itself should theoretically like interact with other fields in the universe or around the path. So after a while, shouldn't you expect that phase like averages out in some way?
Gravitational waves are remarkably weakly interacting with things in the universe. You know, unlike electromagnetic waves, which are interacting rather strongly, and that's why sometimes, you know, it's hard to see behind, you know, dust or behind whatever, some scattering medium. Gravitational waves don't get scattered by anything. They don't, you know, the velocity of their propagation doesn't get affected by anything. They're very immune to absorption, you know, refraction, all these things that happen to electromagnetic waves. And that is part of the reason why there's such powerful probe of the universe and such different probe, is because they propagate, you know, unhindered through the universe without entanglements or anything like this.
Okay, guys, let's do lunch. Yuri will be here today and tomorrow. So